Over the last few videos, we learned how logistic regression finds the best line. But sometimes, the best line is meaningless. Consider this dataset. Logistic regression returns a single line, which technically is the best option. But would you trust that line? It doesn't seem like any line could meaningfully explain this dataset. Sometimes, the best line isn't all that special. Consider this other dataset. Logistic regression again gives us a single line, but there are still countless other lines that explain the data almost equally well. The data isn't convincingly giving us a reason to prefer one over another. That's what we're missing, a way to contextualize the line that logistic regression finds so that we can answer, how much is this line worth trusting over other plausible explanations? As it turns out, we've already built all the tools we need to answer that question. We just need to look at logistic regression from a different perspective. This is how I think about logistic regression. We already know how to compare lines using the likelihood. Lines with low likelihood don't explain the data well. So if the best line has a low likelihood, it might not deserve credibility. But even a line with high likelihood might not deserve credibility if other lines also have a similarly high likelihood. How many such lines are there, and what then should we believe about our data and what it takes to pass exams? Consider that even before we get any data, we may already have some reasonable understanding of the problem, making certain lines more believable than others. For example, we know that studying more than 1,000,000 hours for an exam is just not possible. Similarly, exams won't usually be more than 6 hours long. The point is that without seeing any data, we have some prior belief that already shapes which lines would even be believable to us. The data we observe should refine that prior belief. For the sake of simplicity, let's say for example that after talking with some professors and experts, we believe that there are only 3 possible ways to explain what it takes to pass an exam. Before seeing any data, we believe these 3 lines are the only credible solutions. How credible is each one? Well, we don't have any strong belief about any of them prior to seeing any data, so maybe they're all equally plausible. We can describe that uncertainty using probability. Each line gets assigned a probability that represents our confidence in the line. Since we have no reason to believe in one line over another, that probability is the same for each line, 33.333%. As data arrives, we can update that confidence because some lines become less believable given the data we observed. But by how much should we adjust our confidence in each line? A line should only become more believable if we already considered it plausible and it explains the data well. How well a line explains the data is a quantity we already motivated and measured, the likelihood. Lines with higher likelihood better represent the data. The first data point arrives. This is a student who studied 3 hours and took a 2-hour exam and passed. For each line, we can multiply our prior belief in the line with its corresponding likelihood. Now, lines we already thought were plausible and that explain the new student well become more believable. Lines that don't become less believable. But there's a problem. These values are no longer probabilities since they don't sum to 1. So we divide by the total to ensure that they remain probabilities. That equation might look familiar. It's called Bayes' rule. Every new student updates the probabilities. Eventually, almost all our belief is concentrated on a single explanation. It's the only one that remains plausible after seeing the data we saw. Of course, realistically, there aren't usually only 3 possible lines. There are infinitely many. Having only 3 lines meant we could represent our confidence in a histogram. We can't do that with infinitely many lines, but the intuition is similar. For each parameter, we can generate infinitely many lines and assign a probability density to that set of lines. To make things easier to visualize, let's fix the bias term to 0 to anchor lines at the origin, and look at the probability density as we vary WEL and WST from -3 to 3. This surface lets us see where our belief is concentrated. It's flat for the same reasons the histograms had the same height. We don't have any strong belief that any of these lines is more plausible than any other. But it's a bounded box, so we don't believe that lines outside this box are plausible. Updating our belief is exactly the same as before. As we get new data, we multiply our prior confidence in each line by its corresponding likelihood, and normalize. Nothing conceptually has changed. The only difference is that confidence, previously represented as individual probabilities, is now a continuous probability density being molded and reshaped by data. Something about this landscape should feel eerily familiar. It seems very similar to the likelihood landscape, which makes sense. This belief landscape is determined by our prior belief updated by that same likelihood, in a process called Bayesian Inference. Our prior belief provides the starting shape, and the data does the sculpting. When we don't begin with a strong preference for one line over another, the data, and thus the likelihood, is responsible for the final shape. That's why the two landscapes often end up looking eerily similar. Sometimes, though, our prior belief can influence the shape a bit too much, but we'll get to that. Let's dive deeper into what the shape of this landscape tells us concretely. Consider these 4 datasets. The first dataset is the one we've been working with so far. In the second, 2 students who studied more than the exam's length failed, and 2 students who studied less than the exam's length passed. In the third dataset, the students pass with a probability determined by a specific sigmoid. Notice that the proportion of students that passed on each line parallel to the threshold match up with the probability of passing assigned by the sigmoid. The fourth dataset doesn't seem to show any clear pattern that logistic regression should be able to find. Let's see what the belief landscape tells us in each case. In the first dataset, our belief becomes elongated because many lines explain the data almost equally well. We also notice that the best line is at the edge of the plausible region. Is our prior belief preventing us from discovering an even better line? Or did limiting the scope of possible lines with this bounded box actually save us from searching the space for incremental but meaningless improvements? We'll get back to that in a later chapter. In the second dataset, we find a compromise. The belief landscape settles around a slight peak. It's counterintuitive, but the mistakes our model makes are exactly what drives confidence to concentrate more than in the previous dataset. In the third dataset, there seems to be only one clear solution. The data seems to be a perfect fit for a logistic regression model where the proportion of students that pass exactly follow this specific sigmoid. In the fourth, the entire dataset seems random. But the shape of the landscape seems to be almost the same as the second dataset. The only difference seems to be where it's centered. So what's going on? Why does this landscape seem to imply we have a strong belief in a line when no line seems to be adequate? Recall that WEL and WST represent how much exam length and study time influence a student's chance of passing. The bigger the weight, the more influence each has. Small values means that passing or failing might not have anything to do with exam length or study time. In this case, our belief seems to be concentrated near WEL equals 0 and WST equals 0, which means we believe the influence should be small. What's more, it's a symmetric, bell-shaped surface, meaning we're not sure whether the influence of study time and exam length should be a positive or negative one. So we do have a strong belief that neither study time or exam length can meaningfully help us determine whether a student will pass an exam. And indeed, the dataset as it is shows no discernible relationship. So while the shape of the landscape tells us how much belief we have, location tells us what we believe. I know what you're thinking. Why are some of these landscapes so skinny looking? I kind of expected them to be more round and symmetric. Great question. Remember that we fixed the bias to 0. That means that all the lines displayed on the landscape are anchored at the origin. Most of the lines coming out of the origin don't even pass through the region occupied by our data. Any line that doesn't pass through the data will generate a pretty similarly terrible likelihood. That's why most of the landscape is flat. Let's look at the most plausible line. Having a round shape around the most plausible line means that changing the parameters a little bit still produces a plausible line. But since it's anchored at the origin, this means that either we're tilting the line, or we're changing the weights in such a way that the position of the line doesn't change. Only in the first dataset can we tilt the line and still get good separation between the two groups. And even then, it's a pretty small tilt. These landscapes are skinny because the position of plausible lines when the bias is set to 0 is pretty much fixed. A slight tilt completely changes the likelihood and thus plausibility of the line. So what happens if we change the bias term to anchor the line elsewhere? Visualize the landscape as a function of all three parameters, we'll reuse the trick from the previous video. The color gradient corresponds to the height of the landscape, so we can compress the 3D surface into 2 dimensions. And we can scan the landscape for darker regions. Darker colors correspond to higher confidence. Some datasets concentrate that confidence in a small region around the most plausible line. Others don't. We'd like to measure how concentrated that confidence is by measuring the size and shape of that region. To make things concrete, we can define this region as the set of lines that captures about 95% of our belief. Intuitively, if that region is small, it means most of our belief is close to the best line. If it's large, then our belief is spread out and the best line doesn't quite stand out. Let's zoom into our dataset to understand what this means more concretely. Logistic regression found this line. The region nearby that contains 95% of our belief is like an elongated cloud. To concretely list out all possible lines in that region, we can list out the range of parameters that describes it, which we can do by looking at the shadow cast by the region on each axis. Each of these intervals around the most plausible line is called a credible interval. These intervals tell us how much uncertainty there is in each parameter. But the interval by itself is misleading. Notice that the shape of the credible region tells us how our uncertainty is organized across all the parameters simultaneously. Once we replace that shape with separate intervals, that information is lost. Was the region square, circular, elongated, diagonal? The intervals don't tell us how our uncertainty is organized and shaped. But what does the shape of the region actually tell us concretely? Let's take a closer look. This particular region looks broad along 2 directions, but also slim in another. To understand what this shape means, let's look at the lines nearby. We'll move one parameter at a time. Notice how tilting the line quickly moves the point outside the credible region. But shifting the line, it remains in the credible region for a long time. This difference in how sensitive the line is to changes in each parameter is something we've already discovered. And naturally, it appears again here because this landscape's shape is partially determined by the likelihood and quirks of our data. The data seems to be constraining the direction of the line more so than its position. If the dataset looked more like this, now position is more certain and direction is less certain. But there's another broad direction that isn't explained by parameter sensitivity. That direction aligns exactly with the ridge we uncovered in the previous video. In this direction, the parameters aren't moving independently one at a time. They're moving at the same time, compensating one another to create the same geometric line with different parameters. The same boundary between groups with different probabilities of passing assigned to each student. A broad region in that direction means that once we've found a line that separates students that passed from those that failed, there is uncertainty about the exact probabilities we should be assigning. In practice, we can't visualize the full credible region once there are more than a few parameters. Fortunately, we can capture the local geometry of that region with math we've seen before, the Hessian. The Hessian tells us which direction the landscape changes rapidly, which directions it changes slowly, and how the parameters interact with one another. What previously helped us optimize navigation now helps us capture how our confidence is shaped around nearby plausible lines. At this point, we not only know how logistic regression finds the best line, we also know when that line is worth trusting by looking at a landscape of plausible explanations. A landscape that was sculpted by the data we happen to encounter. But what if we encountered a different group of students? How much would the line end up changing? If it changes a lot, was the line worth trusting? We know how to quantify trust in a line by the shape and location of our belief after encountering data. Next, we'll learn to quantify trust as stability to changes in the underlying data. Like and subscribe for more content like this.